this afternoon's seminar. And I'll introduce our good friend and colleague here, Peter SWARZENSKI from the U.S. Geological Survey. He ranks up high, and Peter's got expertise in a variety of things. He does chemical oceanography. I think your degrees are all in chemical oceanography, basically. And he done a lot of work in submarine groundwater discharge using different types of remote sensing techniques, including electrical resistivity, looking subsurface. It's got hundreds of publications, and it's really a great guy. I'm really happy to have him here today. And I feel remorse because I know that he's actually going on to other pastures soon, going to the IAEA, and he'll have to slum it in Monaco, apparently pretty soon. So today's talk is he's going to speak about examples of his work, some areas from all over the place, west coast of the U.S., Hawaii, Alaska, Marshall Islands. I mean, he's got works in collaborations all around the world with USGS. So.
Thank you, Craig. Well, thanks so much for coming, and Craig, thanks for hosting me. I'm always excited to come here, and it's a lot of fun. So I worked for the USGS on what used to be the Geologic Division. It's in a program called the Coastal and Marine Geology Program, and we have expertise in marine geohazards, sediment transport, coastal marine ecology, and also chemical oceanography and marine geochemistry. And what I'm going to do today is present some work, like a smattering of work, on a project that I developed for the Coastal Marine Geology Program called Coastal Aquifers Project, where we're interested in the physics of coastal aquifers and how they exchange with seawater, but also what's in this groundwater in terms of delivery towards the nearshore ecosystems, and then also its potential role in erosion and cliff stability and things like that. We'll get to that in just a second. But I want to do this really informal, and if you have any questions on anything, please alert me. So here's a web page for this Coastal Marine Coastal Aquifer Project site, and I'm happy to talk to anybody about this afterwards. Students, if you guys are finishing up, Coastal Marine Geology has 3 offices, one in Woods Hole, one in St. Petersburg, and one in Santa Cruz/Menlo Park. And there is always internships and other potential opportunities if you were interested in this. So the Coastal Aquifer Project is designed to kind of tackle some of these broad themes. I know Craig is putting this submarine groundwater discharge topic on in this session, so we're interested in how much water is coming out into the near shore, where is it coming out, and we're developing and using different techniques to try and address these things. As I mentioned, we're interested in constituent loadings. We're working a lot now with biologists to not only say how much, for example, nitrogen is coming into nearshore waters, but how is that impacting, for example, the coral reef ecosystem. So working with microbiologists to try and get better at not just delivering loads, but actually looking at how the corals respond to that. Interested in marine and terrestrial drivers, these hydrologic controls on coastal geohazards, and I'll get to that at the last part of my talk when I talk about some work in Alaska that we're working on the North Slope. And then interested in radionuclide behavior across land-sea margins. And I know Henrietta gave a talk here earlier in this session, and she certainly is one of the world's experts in radionuclide behavior. So I'm just going to touch on that very briefly. So very quickly, physical forcings on SGD. On the terrestrial side, Darcy's law dictates how water is going to flow down gradient. It's made more complicated by the underlying geology. On the marine side, it's more complicated in that you can have waves set up on all kinds of different scales, tidal pumping, current-induced rapid flow, convection cells, and sea level differences. The traditional SGD interface would be identified in this upper left side, where without a change in water level, so with a static seawater, the dispersion mixing zone along the saltwater wedge is primarily the area of salt freshwater mixing. We know that the tides play a large influence on how water moves across this land-sea interface. And on the right-hand side, I think Claire Robinson probably was the first to really nicely show that it's much more complicated than this kind of zone of dispersion, and you get this upper saline, recirculation cell that happens up here. Here's a zone of fresh water coming up, and then you have the freshwater saltwater interface, the salt wedge, on that end. And I have one example of this from some work we've been doing in Puget Sound. So this is in the state of Washington, very large tides, 5-meter tides, but very protected in the sound. So you don't have a lot of winds, and basically you just see, it's a great place to look at just the water moving up and down and how that impacts the flow of groundwater out to the coast. And so the upper panel here shows a multi-channel electrical resistivity image of the freshwater saltwater interface, and it shows this upper saline cell, the area of groundwater coming out, and then the saltwater wedge. And then the bottom shows the same area, the same cross section across the beach, but it shows a much more tedious way of getting the same information. And we installed these piezometers, and each point represents a single point sample, and then we would measure salinity and other constituents. But you can see really nicely that in this particular system, you get this upper saline cell, the zone of freshwater coming out, and the marine influence. And so if you're interested in Puget Sound, for example, in nitrogen, how nitrogen impacts eutrophication, it's important to think about what's going on in the subsurface, and the scales here are 5 to 10 plus meters down. And so if you happen to be sampling, anywhere along this cross section, you're going to get different values in terms of the nutrients coming out. Yeah.
Is there some sort of boundary as a hot
So this is as far as we went when we did our piezometer sampling. There was certainly we're looking at the shallow aquifer coming out into Puget Sound. There's a deeper flow system that it connects with, so there's a bottom boundary as well.
Yeah. The across beach face, does that mean from offshore or?
No, and I'll show an example of this in a little more detail later on. But basically, this is in the uppermost part of the beach, and then this is moving out across the beach. And the tidal range here is probably the high water mark is close to up here, and the low water mark is down here. And at low tide, you actually have little geysers of fresh water that come up because of the change in the hydraulic head. So that was an area that didn't have waves. There was just this bathtub model of water coming up and influencing the freshwater saltwater interface. This also happens in waves, in wavy environments. And this is shown here where you have this upper saline cell, an area of groundwater coming out, and then the freshwater saltwater interface below that. And so this dynamic mixing of how groundwater comes into the coast is really complicated and is influenced by all kinds of different driving processes. And on that note, I thought I would, Cliff Boss, for those of you guys that know him, is probably the father of variable density flow models and has worked on these models all over the world. And I think he did a really nice job kind of adding a sense of reality to these models. And we all know that models can tell you almost anything you want to, depending on what you put in. But he has a sequence of 3 or 4 slides that I think are really useful when you start to try and interpret what is happening. And so, based on Darcy's law, a simple groundwater body is going to reflect a topographic high. We know that it's going to move from an area of high to low. That's quite simple. It can be more complicated because you're not just going to have one topographic high, you're going to have multiple ones, and you can come up with these conceptual flow paths. The big assumption here is that we're assuming a uniform hydraulic conductivity, or K. In reality, it's never that simple, and you can have areas of high or low K that are going to influence these flow paths. For example, if you can envision this as a fault or as a road, it's going to have a large influence on these flow paths. And then our own imprint, in terms of pumping water, groundwater up, are also going to affect the flow paths. shown in this sequence of slides here. And so when you design a SGD study and you're interested in the flow of groundwater to a particular coastal area, you have to, you have to think about all these mechanisms that might be going on in the subsurface and how complicated the actual flow of groundwater is to that site. And as we know, we can, for example, measure the groundwater discharge rate for one area, and you can move over a few tens of meters, and it will be, or even meters, and it will be totally different. So I mentioned that we use naturally occurring radionuclides. I have one slide just as a quick summary. There happens to be 6 or so isotopes of radium and radon that are great geochronometers. They range from radium-226 that has a 1600-year half-life down to a really short fluorine that has a less than 1 minute half-life, and I'm going to have one example of the utility of fluorine as an event groundwater tracer off of West Maui. But basically these are all little time pieces that are clicking away at different times, and because they're naturally occurring, you can look at ratios of, for example, 223 to 224, or radon to radium-224 as unique timepieces to try and get at the kinetics of a particular rate. So here's some of the projects that I want to highlight today, and I'm going to go through these really quickly. I'm going to start with Santa Barbara, talk very briefly about Malibu, then I have some examples from Hawaii, from Oahu and Maui, and then I have just a few slides on Puget Sound, and then have a few slides on the Marshall Islands, and I'm going to end on Alaska. So Santa Barbara, the issue here was that it's a popular beach. People like to swim and surf, and the city of Santa Barbara asked us if we could find out if there's a groundwater vector for bacteria coming into the North Shore waters. This is the main harbor. There happens to be a shore parallel water stormwater drain that's built that actually winds up playing a big role in moving nutrients towards the beach. And I just have a few highlights here. So we did a lot of different things. We set up these electromagnetic seepage meters. We did time series radon, as I'm sure Henrietta showed you. We did streaming resistivity profiles. We did radon surveys. Basically, the schematic of the beach, the cross section, looks as follows. We installed a series of wells to try and tap into the different aquifers coming out towards the beach. And this storm drain is shown here. And the storm drain was installed. It's actually typical of many coastal cities in California. It was installed more than 50 years ago. And there are these cement sections that are roughly 4 to 6 feet in diameter. And the sections often leak, and we actually got the city to put in this camera system that moved through the storm drain. You can actually see where it's leaking tremendously. So in the rare event that you have a big rainstorm, the storm drain will fill up and then provide this kind of localized hydrologic high where then eventually the water leaks out into the beach. So just a couple of snippets from Santa Barbara. The first slide here is conductivity, water levels in blue, and basically at these low tide events you get peaks in radon, and in these electromagnetic seepage meters from which you can calculate a groundwater discharge rate. In Santa Barbara, the groundwater discharge rate was not very high. It was averaged around 3 centimeters per day. So orders of magnitude less than what you would get here. One slide to show the utility of these different radium isotopes and radon to first get at mixing ages, and the natural log of these isotopes as a function of distance from shore allow you to get at a mixing coefficient, and then multiplying the mixing coefficient by the radium-226 gradient, remember that's the longest lived radium isotope, allows you to calculate a flux of groundwater. And then on the right-hand side, this is following what Henrietta pioneered in Thailand, plotting radon and radium-224 as a function of the radium-derived apparent agents allows you to get at an independent assessment of how much radon, which is a noble gas and likes to escape into the atmosphere. That's one of the important terms that you need to know in developing a groundwater model. So moving to Malibu, so this is a little bit further down coast. Malibu is a very famous surf break, and again, the city was interested in trying to find out. People had been reporting bacterial infections in their ears, and the city of Malibu was interested in finding out if there's a groundwater mechanism for pushing bacteria into the nearshore waters. This system is interesting in that the watershed of Malibu, I think this is a photograph that kind of shows how large the watershed for this Malibu Creek is. The unusual thing here is that the berm can either be closed or open, and during the wet period, as shown here, the river floods the berm, it cuts through the berm and discharges into the nearshore waters. During dry seasons, you get this pretty expansive berm, and it's, as a consequence, the bottom water oxygen concentrations go to zero, it turns anoxic, and there's all kinds of interesting chemical reactions that happen then in this backwater. And because it sits higher than the ocean water, it gets pushed through the berm. And in that process, it actually cleans up some of the microbes, some of the larger microbes stay behind and get filtered, and then some of the bacteria make their way out. So there's an interesting microbial story with SGE. We were challenged in that typically you set up a mooring platform to measure radon over several tidal cycles from which you can get an SGD rate. When we were here during one of our field trips, there was a 10-year storm that had produced these incredible waves, and it was no easy task to try and set up a radon time series. We actually used the wheel from a railroad car and made sure that that stayed stationary, and then used an intake and ran it, buried it up on the beach. But we got really nice data. This is shown here. So this is in blue again, the tide, and you get these big spikes in radon. And as I'm sure you've seen, these spikes in radon can be used to calculate a groundwater discharge rate. Here's a schematic that kind of shows the lagoon with a berm in place.
Peter?
Yeah.
How do you put these wells in on the beach? Do you have a truck-mounted rig or something?
We don't. We do them by hand. I have a gas-powered auger where two people drive it down. And we also just, with brute force, you just hammer down on it.
And you can get 3 meters down?
Yeah.
Congratulations.
I'll show you, in Puget Sound we got down to 10 meters.
Nice.
So here's what it looks like if you drape a resistivity cable over this berm. It allows you to look at kind of these preferential flow paths. And this is interesting. People are interested in this, for example, trying to find out if this contaminated lagoon water, stagnant lagoon water is leaking out. The resistivity will allow you to find out where it's actually coming out. One last slide from Malibu. The barrier acts as this interesting biogeochemical reactor, and I think I mentioned this. A PhD student from Santa Cruz that I work with, Priya Ganguly, who's now at West Hole, did a really nice study here looking at the monomethyl mercury story in the berm and in the lagoon. And so she was able to tie an SGD monomethyl mercury story for Malibu. But basically, the two slides over here, I think, tell the story nicely in that blue is the water level, black is surface water nitrogen. At low tide, you see this big increase in nitrogen. And then looking at the CNN ratio in red, you can see it goes up dramatically as the tide goes in. As the tide drops and the role of groundwater becomes more important. All right, the next slides are closer to home. First one deals with Mauna Loa Bay. I was lucky enough to start working in Mauna Loa Bay as my first study site in Hawaii. And for those of you that have worked in Mauna Loa Bay, this is like, there's so much groundwater coming out, focused groundwater coming out. It's a joy to work. It's relatively easy, especially coming from California. And so here's for example, what the radon profile looks like from Mauna Loa Bay. First of all, if you just look at an image at low tide, you can see tons of groundwater coming out and causing these little erosional features. That's a sure telltale. But here's a radon profile over several tidal cycles. In blue again is a tide, and at each low tide event, you can see this very sharp needle in radon. Concentrations are tremendously high, and from those you can get a radon-derived advective rate, and as you can see here, it comes up with 300 centimeters a day as a maximum, not as a mean, but as a maximum. So radon works beautifully as a groundwater discharge tracer for Hawaii. The next sequence of slides is something that Natasha Demova did, and she laid a resistivity cable across a beach where there was lots of groundwater coming out, and I'm going to show you a run from kind of mid-tide down to low tide, and the hot colors here indicate more resistive material, and in this case we're tracking kind of a freshened water parcel, and you'll see the shape of this changes as you drop down. So here's approaching low tide. You can see the shape of this gets larger. The y-axis here is looking down into the sediment, roughly 10 meters, and then looking out across the beach face, roughly 100 meters. And you can see how the groundwater plume gets stretched during low tide. And actually there's these springs that occur, and you can see manifestation below the surface water. The next series of slides deal with West Maui, and I know a lot of you guys have worked in West Maui. It's a really interesting place to work. There's a Lahaina reclamation site, wastewater reclamation site, just upstream and in direct flow paths to where there are some submarine springs very close to shore. And in this instance, I'm not so much interested in what's in this groundwater coming into these nearshore waters, but trying to see if we can develop some techniques to utilize thoron as an event groundwater tracer. So that said, if you stick a piezometer point into the spring that's discharging, the groundwater concentrations are much, much higher than the surface water concentrations. And if you swim around, you can certainly note that the coral reef has been dramatically impacted by this persistent upwelling of tainted groundwater. So we set up a series of different instruments to try and help us look at the physics of exchange. We set up thermistor strings, and I'll show you an example of some of that data in just a second. Wave sensors, ADVs, and actually developed this little articulating arm with the hope of actually putting this directly over a vent feature so we could use that to measure discharge rates in very high resolution. We had ADCPs to measure currents. Here's what this ADV looks like. Here's some data from the thermistor string. So the primary vent site is roughly 20 meters from shore in about 2 meters of water. And we set up this triangle of thermistor arrays. The water depth is really shallow, and so depending on where you go, the waves can actually be pretty dramatic on the west side of Maui. And so what we're able to show here is these different temperature arrays, and in blue you can see that's the data from the primary vent site. At low tide, this is approaching low tide, you can see lots of warmer water discharging out. And I think what this is showing is that there was actually a large swell event before we went out in the field, and this is in kind of the discharge of the aquifer system responding to this infiltration from the large swell event. This is my collaborator, Kurt Strelazzi. He's a physical oceanographer, and you guys know, I'm sure. He set up some of these ADCPs, and the point was to not just measure how much groundwater is coming up, but then to be able to say how the ocean currents are pushing this plume of more buoyant fresh water in the surface waters. And So without going into a lot of detail here, you can see the gray are near surface, the black is near seabed. There's this consistent push southward during the time that we were out.
Is that modeled or observed?
Observed. So the next couple of slides deal with this idea of trying to use boron as an event tracer. It's all based on this RAD7 radon detector, which is commercially available. It's relatively inexpensive, and it was originally designed to sniff for radon in people's basements. But by knowing the partitioning coefficient between air and water, you can develop this simple extractor or diffuser. We use a bilge pump or a peristaltic pump water into this. It kind of sprays the water, and then an airstream gets eventually routed into RAD7, and you get a radon signal. The RAD7 actually doesn't just give you radon, but it gives you, it also can give you thoron if there's enough activity with thoron. And the way you can concentrate or maximize one of the RAD7s to measure for thoron, in this instance I had a separate RAD7 and we installed this additional air pump. This is what it looks like on the boat. You can see how close, we're sitting right on top of the primary vent, and how close it is to the beach. Here actually it was pretty common, but as luck would have it, the waves break right about where the boat is. And so if there's any swell, it gets exciting. Here's what some of the data looks like. Top is tide. Here, actually, we're able to pick up salt water being pushed into the bedrock, and then you get these little spikes just at high tide in salinity. Here's what the groundwater radon concentration is, and we need that as an end member in our calculations. You can see it stabilizes, and then here's what the surface water radon looks like. And again, you see these spikes coincident with the low tide events. And you can come up with a mean advective rate of around, say, 90 centimeters a day using radon. And let me just mention, so this RAD7 is set up to measure different isotopes of polonium, which is shown in this window, in this illustration here. So now for thoron, it has a 56-second half-life, so a really short half-life. So the only way you're going to actually see it in seawater is if you're very close above the source. In 5 minutes, you won't see any thoron. It will have all decayed away. And so I set up the RAD7. I would turn it on and off at a known frequency to try and make sure that I didn't overwhelm the signal, but also was able to capture the thoron signal. And so here, these are the radon concentrations over one low tide event, and then I converted these into a inventory knowing the water depths, and I came up with an SGD rate. I don't know if it's on here, but it was actually very comparable to the radon derived SGD rates. Okay, so now moving to Puget Sound. I've spent a lot of time working in Puget Sound on trying to develop kind of this geomorphic typology of SGD. This map over here shows the extent of Puget Sound. This is Hood Canal. Many of these canals are really deep, and as I mentioned, the tidal range is huge. The data that I'm going to present come from this little area here, which is this terminal of the terminus of a fjord called Lynch Cove. But we've worked in many other areas shown by these dots. And we're trying to divide up the shoreline into rocky shorelines, beaches, embayments, and river deltas. So the first couple of slides come from Nisqually. Nisqually is towards the southern end, kind of by Tacoma. And when we first got there, we had talked to some hydrologists who thought there would be the greatest chance of getting into some SGD, looking at this site here. There's a glacial moraine that terminates in this area. We happened to get out there at high tide and did not see very much at all. But at low tide, we found this big submarine spring. And here's our radon boat sitting at low tide. And you can actually, we hammered in a piezometer into the throat of this spring to get groundwater data from that. The salinity was between 1 and 2. So even though we, it was really colly and you really couldn't get a deep well into this, we got, even at, even when at high tide, when the ocean level was up here, we got consistent salinities of 1 to 2 from this piezometer. But you can see there's unique biological adaptations to all this groundwater coming up. And in Puget Sound, people are very interested in habitat for fish like salmon that often seek refuge in areas where there's groundwater coming up. They call them pocket estuaries, that they're often bound by berms, and there's a significant amount of groundwater coming up. So here's what the radon data look like for Nisqually. You can see really pronounced spikes in this really large tidal range. So now moving towards Hood Canal. This is Lynch Cove area of Hood Canal. I wanted to just show one example of using electrical resistivity to try and get at the plumbing underneath a particular beach face where we know there's lots of groundwater coming out. So that's this transect right here. This is what it looks like at low tide. Lots of groundwater, as I said, is discharging out. Here's our electrical resistivity cable. And here's what some of the data look like from this. And there's a seepage face that you can see here, and it allows you to look at kind of these zones of enhanced flow over these scales. So I think this is really a useful tool to try and get at the freshwater saltwater interface in the subsurface to useful scales. In this case, we're going down 25 meters or so. I mentioned pocket estuary. So the idea is that because of the great tidal range, you can be the tidally modulating SGD zones with obvious implications for these fish habitat. So the last two slides from Puget Sound are an example of some of the wells that we installed. Chip, you had asked about how deep these wells would go. So we worked along this dock, and we installed a series of piezometers and also wells shown here. So we went down 9 meters, 10 meters in some of the wells. And this is the kind of data that produced that salinity profile that I showed earlier. We also set up, I think we have 4 different RAT7s going from each one of these wells across the beach face. We measured radium isotopes in each one of the wells, and then did typical trace element chemistry on all these things, and these are being worked up right now. Okay, so we're almost done with this geographic tour. The next 2 sites are the Marshall Islands, and then I'm going to end it with the North Slope of Alaska. Oftentimes, I guess for the last 3 years or so, I've had this project with collaborators at UH and Kurt Strelazzi in Santa Cruz on the Marshall Islands, specifically in Roy Namur, and it's a military installation, and they are very proactive in trying to find out how potential sea level rise scenarios are going to impact their installations. And so Hawaii, somewhere over here, Hawaii is about equidistant from the mainland, so it's another 5 or 6 hour flight to get to the Marshall Islands. This is what Roy Namur looks like. It's interesting in that this is Namur. Roy is almost devoid of any vegetation, and that has implications for the hydrologic budget, but then Namur actually has been left alone. And so I have a student right now who's looking at the hydrochemistry of these two islands, these contrasting islands. And I'm going to present some data from some different areas here. But let me just say that the different components of this project, the UH component is modeling climate change scenarios. We have a NOAA contingent that is doing some nearshore mapping. The survey with Kurt Strelazzi is looking at modeling inundation, so wave-driven inundation. And then I'm working with Steve Gingrich and Cliff Voss to look at how the hydrology is going to be impacted by sea level rise scenarios. This is what some photographs of what Roy looks like. This is a good example of how close this is high tide, and you really only have about a foot or so before it starts breaching on it. And so it's not uncommon, I think, for water to come over. And I'll show that as an example in just a little bit. Here's kind of a hydrogeologic cross-section of Roy Namor, and as I'm sure most of you know, these atolls are really interesting to model. You have this Holocene, you have this nice kind of two-box model, Holocene deposits, and then these much more permeable Pleistocene deposits. A little freshwater lens sits on top, moves up and down, it floats on top of the seawater, and we're interested in the vulnerability of this freshwater lens. So I have two examples of resistivity. One of them is from down here, and then the other one is, yeah, it's ABOS. So in red, you can see the unsaturated zone. It's about 2 meters deep. And then in green, you see the fresh water, and then in blue, you see brackish seawater. I did a high tide, low tide example. From here, you can see how there's no fresh water, obviously discharging into the near shore, but you can see the influence of the tides on this little coastal aquifer. And then here I have pore water salinity profile, and I'll show an example of that in just a second, but basically you can see from 2 meters to about 4 meters, you're in this freshwater zone, and then very quickly from 4 meters down to 8 meters, you transition to seawater. The bottom slide, I think, is a good example of how heterogeneous these islands, these atolls are. And if you think about how they're building, oftentimes they're building from an overwash event, so they consist of cobbles, and it's really quite complicated. And Steve Gingrich with Cliff did this very density flow model, and from an overwash event, they tried to figure out how long it would take for the little freshwater lens to clean up, and the only way they could do it is with these strong vertical exchanges that have to do with the heterogeneity of this depositional environment. So here's some pore water profiles, and we used a gas-powered drill and a 1/4-inch stainless steel rod, and we're able to get down to 8 meters here. So the unsaturated zone and saturated zones, salinity, pH, and then some trace elements. And you can just wanted to show these as a nice example of these different water bodies and the mixing between these two. So one of the times I went out, I think this was after maybe an ocean sciences meeting here in Honolulu. I went out to the Marshall Islands, and I was lucky enough to capture this overwash event. And I met this guy in a bar the night before who said, "You should come fishing with me. Fishing is phenomenal out there." So I went with him, and when we went fishing, there was a big swell, but there was no wind at all. It was a beautiful day, but we came back into dock around lunchtime, and then high tide struck around 2 o'clock, and I was able to capture these images. And of course, the locals weren't so excited about it, but for us studying this, I think it was pretty exciting. There was actually fish that had washed over. And this, the big thing is this used to be a once every 10-year event, and this is happening now every year, multiple times a year. And I have just some representative examples of how this overwash event was recorded at the groundwater levels. So I have a series of wells that I installed both along a beach and then interior, and the overwash event here in blue is a tide. You can see the beach piezometer jumped up significantly, and then even on an onshore piezometer, so this is probably 100 yards inland, you can see the effects of this overwash event. And to counter that, we were there during a really hard rain event. They had an unusual, I think it was a tropical depression that caused lots of rain directly over the islands. And you can see how in green here is the water level. This is the groundwater level, how much it surged during this rain event. So this little freshwater lens is extremely sensitive to external perturbations. Yes.
How much alteration, dredge and fill, et cetera, do you think there was?
I mean, Roy was bombed like crazy. So one analogy, like this whole island is dropped from some elevation, and they've done a lot of things to it. I mean, it was hard. It took me a long time to get a nice resistivity image because I think there's so much stuff in the subsurface. Ironically, we actually found a Japanese hand grenade when we were drilling, and I had to call Kurt Strelazzi got all excited. We had to call the MP and it's sectioned it off. But it was yeah. So here's some results from Kurt, and I actually got these this morning from him. You know, he's really interested in modeling sea level rise scenarios, and so this is not just a bathtub model, but this actually, they use cross beach, and they're interested in the wave, how waves are going to impact and exacerbate the flooding, and under different sea level rise scenarios. And I just took mean high water, then a 150 centimeter sea level rise projection and a 2 meter sea level rise projection. And I think the bottom line here, you know, as is in the news all the time now, the Marshall Islands are really ground zero for climate change impacts, and are going to feel it immediately. All right, so the last series of slides deal with this project that I've gotten roped into in the North Slope, and it's totally different than the Marshall Islands, but I'm really intrigued by it, and I have a lot of unanswered questions, and I would like to hear your input on this. But our office has been involved with shoreline change for a long time, and Bruce Richmond and company have been going up there for a long time, trying to evaluate how the shoreline of the North Slope of Alaska is changing over time. And Barter Island is one of the few places that you have access to relatively easily. Alaskan Airlines flies there, but it also is a site where there's lots of erosion. And I got roped into seeing if we can see if there's a groundwater role in contributing to this erosion. So here's what this island looks like. There's, out in the distance, you can see just a few houses. There was an old dew point site from the military. The airport is literally on a little barrier on the beach down there. But you see tons of these kinds of images where there's obviously the coast is in dramatic retreat. I think erosion rates could be 10 plus meters a year, and obviously very dynamic. And I showed you a lot of examples of electrical resistivity profiles across different beach faces. The same technique actually works really well to look at permafrost deposits. And I've been working on an LTER site in Fairbanks, where we first tried this out and it worked beautifully. So I thought it would be neat to see if we can get anything interesting here. First, before I show some of those results, I wanted to set the stage with this erosion. This is Ann Gibbs' work and Bruce Richmond's work, where they did LiDAR surveys along the beach and then looked at the change from one shot to the next. And I think these are just from July through September, so one summer thaw event, I guess, and you can see how dramatically the beach has changed. So, permafrost obviously plays a huge role in the stability of these coastal bluffs. In general, this is a map of the permafrost distribution. The further north you go, the more continuous permafrost is. Fairbanks is here. It's discontinuous, and then further south you kind of have no permafrost. People have measured the depths of permafrost up here being 400, 500, 600 feet deep. This is what Barter Island looks like. It's bounded by two large rivers, the Hula Hula River and the Jago River, both stray in the Brooks Range, and are ephemeral large rivers. During the winter melt, these rivers are huge, and then later in the year they kind of dwindle down. It's becoming really popular for people to be dropped into the Brooks Range and they kayak these rivers. But anyway, here's Barter Island. You can see a sequence of lagoons, and I think these lagoons will actually be important in concentrating chloride and other things. We know that lagoons affect the salinity regime of coastal waters. So that I think is going to be important. And then the study site that I'm going to show you some examples of are here. Here's what a LiDAR image of Barter Island looks like, and immediately you can tell it's something that's different than a lot of the other coastal areas. In fact, it's much higher than the surrounding mainland. There's not a scale here, but the white basically is 8 meters, and then you go down to the coast. So there's an 8-meter topographic high, and then you can see this is a lake called Freshwater Lake, which the town of Tovik that sits here gets all its fresh water from. When I was up here this summer, we got to talk to some of the locals, and they said that this lake, very rarely, but it does go salty, and they were trying to think, well, maybe during a big storm there's enough salt spray that gets in, but we simply found that there's another mechanism for introducing brines into the bottom. And then you can see this is maybe an old feature of this, and even up here. So we set some thermistor arrays into the bluffs, the first one close to the bluff edge, the second one a little bit further in. The first thermistor was at 50 centimeters, at 100 centimeters, 200 and 250. And basically we were trying to see over the course of one summer what the temperature regime looks like. You can see at 50 centimeters here, it comes above zero. But on the bluff's edge, it comes above zero almost consistently for the whole summer. This spike in temperature, I think this is just thaw water moving down into the thermistor array. So here's what some of the resistivity profiles look like. From the images, other images that you saw, the red here would indicate material that is frozen, so sediment that is frozen. And then the blue would indicate some marine salt water in the sediment. So this is typically fresh water and then salt water. And we went out in 2014 in June and in September to try and see if we can see the effects of one summer thaw event on the active layer and on the permafrost. So this is a shore perpendicular line. Here's a shore parallel line, actually coming down this hill. And you can see here that this pool of salt water is much more expanded here. These features are likely ice wedge polygons, and actually when you walk along this thing, you can see crevasses and large topographic features that are indicative of, I'm really sorry. Indicative of these complex freeze-thaw processes. One more example, and this is looking out, draping a cable over one of these bluff edges, and the first thing that I think is interesting is that this strong contact between, that the resistivity picks up is right at the toe of this bluff, and then from June to September, it it's dramatically different. And so we wrote this up kind of just setting the stage. Well, we need to go back and do some ground truthing to figure out if these resistivity images, these ERT profiles, are an artifact of the inversion process, and that you have this really resistive layer, and it's much harder to see through that. And so we wanted to go back and do some drilling. And here's an example of the drill rod. We actually got down to 8 meters in this case. It was a challenge. Barter Island is this native Alaskan village that has a very traditional whaling season, and the polar bears come into this town during the whaling season. And it used to only be just a few polar bears that would come in, but now, because there's a lot less food and because the ice is so much further back, there's around 40 polar bears that come into this town. So we had to hire a guide to run around on an ATV to keep the bears kind of away from us. And oftentimes it's that foggy, so you really can't tell. But I just wanted to show this. This is an example of you start drilling and you get these peat layers, and then in this instance we got into pure ice. I mean, you can make a snowball out of this. So this was drilling into one of these ice wedge polygons, and then below that you get really old clay. And I'll have a movie that I want to show you in just a second. But there, the depositional environment I think is really interesting here. So quickly, some results from this drilling that we did this summer. This is chloride as a function of bromide, and in red are the seawater mixing line, and in blue are the pore water data. So this would suggest that the chloride data from the pore waters fall in line with seawater. If you look at sulfate as a function of bromide, sulfate is strongly reduced. So I think this suggests that the presence of sulfate-reducing bacteria that are chewing the sulfate. Here's what the chloride pore water profile looks like. So the y-axis is down to 700 centimeters, and the red and blue are just two different drills sites that we did. But you can see the pore water profile goes above 19,000 milligrams per liter, which is the seawater, at around 5 meters or so. So you can put this into this model. We also age dated the sediments. So at 2 meters, age date was roughly 10,000 before present. At 4 meters, it was roughly 25. At 5 meters, it was roughly 31. From that, you can get a mean sedimentation rate of around 20 centimeters per 1,000 years. This falls in line with some of the other results that have been reported from the Alaska North Slope. And here's the chloride concentrations. But it gets more complicated in that we also looked at pore water strontium isotopes. So this is 87, 86 ratios. Seawater concentration is 0.709 consistently. And these values that we got here at 2 meters, 4 meters, and at 6 meters do not suggest that it's a marine source, but rather that it is some erosional material coming from the Brooks Range. And so what we're doing now is taking the solid phase and looking at what's lattice bound versus what's scavenged on the outside. Okay, so before I go into the summary, I wanted to show you this movie. So this is looking at one of these erosional features. I really don't know what's on the soundtrack here. But like at an iceberg cavity, you can see that over the course of one day, there's huge amounts of material that's slumped away. But you get a feel for this active layer that's really organic rich, and then these marine clays or clays. So this is in a little ravine, and you can see the beach just outside of that.
What's the origin of the clays?
Jim Hine ran X-ray diffraction on it, and it looks like it's, I don't know, possibly marine. It's not a sure thing. a lot more work.
And are your dates from in that layer?
Yeah, yeah,
The radiocarbon?
yeah. You know, so the big question is this 30,000 years ago, where was sea level? Was it, 50 kilometers out?
Way down.
It's way down, right?
Maybe you're not dating. I think you have to worry about what exactly
you're
you're
dating.
dating.
Yeah, I mean, I guess you could look at forend or something and try and date the forend. We just did bulk, but it corroborates what's in the literature in terms of age dates.
Not percolation, like,
How do you mean?
Oh.
well, you know, the glacier melt. It's
Yeah.
typical to have a percolational plate deposit out there.
Yeah. I mean, it's really complicated because there's areas that are still frozen here. Some people think that they're relic glacial deposits or even toe of the glacier. But isotopically, we haven't been able to show that. Anyways, so that's. All right, so just my last summary slide. The resistivity is a great way to look at freshwater saltwater interface, or in Alaska to look at the interactions between the active layer of permafrost and ice wedge polygons. Radon and fluoron are great tracers for looking at groundwater discharge rates. Radium can also be very useful. Radium often allows you to look at the saline contribution of groundwater discharge, and then the utility of time series groundwater data to assess forcings. And then obviously any kind of ground truthing, I think, is the more ground truthing you can do, the better. And I'm going to end it with this slide, and that is work that we're supposed to do this coming Monday. This is just north of Santa Cruz, maybe 10 miles north of Santa Cruz, and close to a little town called Davenport. But in the Monterey Formation, there are these seeps, and the seeps consist both of hydrocarbons and water. And the idea is that we're going to attach a series of spikes that we can leave out, and we can clip our resistivity cable to maybe monthly. And with the coming El Nino, try and look at the seasonality of seepage. So I'm going to stop there and see if anybody has any questions.
Thank you.
Yes.
This image is up actually. So are you doing a vertical profile?
Yeah.
You'll be mounting the cable vertically?
Yeah.
Cool.
Is that hydrocarbon from dark stuff?
Yeah.
This looks like, we were talking about this last night, it's like persolite. A lot of solution stuff.
I mean, it looks like sandstone, when we try to drill it to get ready for putting these spikes in.
Well, was it green?
It's brown. It's like,
Oh, I haven't seen that.
yeah.
And then you can see fractures and things in there.
Yeah, so this is, this seepage line is following the fracture down.
Monterey is notorious for that because it's biosiliceous and you get these fractures that cut through it, and that's actually where the groundwater and hydrocarbons are housed in these fractures. As a matter of fact, one of the ways, it's not fracking, but they've been doing it for 50 years in Monterey. They put dynamite and stuff in there to increase that fracture
Oh.
process. Because they're running that way.
So do you think there's a seasonal signal to the seepage? Yeah.
But all along the coast, the petroleum seeps out, all along California.
Yeah.
Tarring your hair because
Yeah.
people always blame it on oil rigs, but it's actually.
There's tons of
right
natural
out of the rock. Sure.
What's the situation on Maui with all the limu washing up on the beach, and the the decline of the reef and pointing of fingers to groundwater or to well injection of the sewage.
Yeah.
How's all that played out currently?
Currently,
Currently, yeah. I mean, who?
legally,
Yeah, legally.
the judge has basically ruled in favor, saying that there's, you know, I mean, it's been clear for a long time, right? Scientifically, you're talking about the wastewater injection.
Right.
It's flowing out along seeps along the coast, and, you know, since we poured dye down there to conclusively demonstrate there's a hydrologic connection, and dye, you know, was coming out in the seeps as well, and so we can put the mass in, et cetera. So that's pretty good. So, about what the corals are doing, that's a whole nother, you know, corals are corals, right? There's all kinds of stuff that's happening upon them. The fish are, you know, they put a fishing moratorium in there, and so,
So how is the county responding with their sewage treatment?
I don't know what the latest, you know, so they're coming to a settlement, and also I would, you know, do I have to go to court or not, right? It's my main interest. But I think they're reaching doing arbitrations of some kind, I don't know about that. Anybody else? We're up on.
So actually you were saying that as well, are interesting to model in terms of groundwater. And then looking at more, I was thinking about the Republic of Kiribati, the article we were supposed to read, and it said that those 33 islands are highly ever higher than 2 meters above seawater level. And then we saw from Moore that the freshwater lens is something like 2 meters. And I was interested in your opinion, because the article was like very teasing. They'll die up first before we die
Oh,
of
yeah.
sea level rise. And I mean, it seems like the freshwater lens, at least looking at Moore, is significant to supply enough fresh water. So what's your point of that?
So Moore is totally manipulated, right? Because it's a military installation. They actually have a huge desal plan. They artificially recharge the aquifer based on the PhD work of Steve Gingerich, who recommended that they recharge the aquifer. They're actually doing it. The Water Management Agency is doing it, and I could show you some photographs where they have these huge fire hydrants that are just running all the time, putting water back into the freshwater lens to stave off saltwater intrusion. And so that's not a good example because it's not natural. You know, it's military, so they'll never have to worry about groundwater resources there. They'll be able to build or do however they want to machine things differently. But another island is definitely, it's this little freshwater lens is incredibly fragile and sensitive to overwash events, and from these modeling exercises, once an aquifer has been breached, when saltwater has gotten in, it takes a, you know, depending on how much it's being used and how much it gets replenished, it can take a long time for it to be cleaned up.
So, in your opinion, it's actually a real threat, the freshwater availability compared to, future sea level rise?
Yeah, I think so.
On the same island, what do they do with wastewater?
They have their reclamation. They have a wastewater system.
And then
You know,
they
there's hardly
interact
anybody
with-
there. There's maybe 100 people that are permanent, and it's Kwajalein is a larger island. It's the bottom of this atoll, and just the island just north of Kwajalein is called Ebay, and that's been called the slum of the Pacific because so many people who work in Kwajalein live there, and it's incredibly dense and contaminated. And so Moore also has a little island just adjacent to it where people live and then can work on Moore. And when you go there, their well is, it's really sad. Their well is totally contaminated. It's not hygienic at all. their water supply. They, rather than actually install a water system that works, there is a boat that comes constantly from Roy and Moore that brings water, and you can see people just, there's one leaky container or leaky pipe after another, the water is just continuously lost. And it's just, it's cheaper for them just to bring water in 2 times a day. So not very much infrastructure at all on the environment. Yeah.
So at all of these sites that you talked about, how do you foresee that climate change and sea level rise, most importantly, will affect groundwater discharge?
It all depends where you are. In
Right.
California, there's not a whole lot of room in many places. So with an increase in sea level, you're oftentimes up against either a city or a cliff or something. So there's not a lot of room there. In Puget Sound, it's so diverse. You know, you have very large rivers that form these expansive deltas. There's this interplay between agriculture and restoration. Some of the largest restoration projects that are going on in the country are actually happening in Puget Sound. So they're trying very, you know, they're doing a lot to try and prepare or, you know, just to manage smartly. Yeah.
For a lot of your different case studies, you compared high tide measurements or lack thereof and low tide measurements. Is that because there isn't submarine groundwater discharge during high tide for some physical forcing mechanisms? Or is it that there's just so much other stuff going on that you can't, as of yet, get a good measurement?
No, that's a good point. So when I go out, I'm usually only there a week or so that's a downside that I'm not there very long, and it's hard to put it in kind of a larger hydrologic context. But oftentimes SGD, it's almost always it happens most at low tide, and oftentimes it's reversed at high tide, so you don't see the signal at all at high tide. And if you go back 50 years or so, many of the large cities along our coasts had lots of groundwater coming up. As an example, Tampa, there's all kinds of evidence that there's coastal springs in and around Tampa, but our own groundwater withdrawals have reversed a lot of these springs, so there's a lot less that's coming up now.
Probably a good place to stop and do some come back. Thanks, Peter.
Please make sure you sign up for that sheet. Where is it now?